Well, thank you very much for coming. I hope you'll enjoy this talk. This is probably the talk with the most slides I ever did. So I'm going to have to speed up a bit, and it's about a performance, so that should work out. So a bit about myself. I'm Marc Lemburg. I've been with Python for a very, very long time, as you can see. I have a company, Egenix. We do Python projects. I'm a Python core developer, Software Foundation member. I'm also a member of the EuroPython Society based in Düsseldorf in Germany. And I do coaching and consulting. And what I want to talk about today is how to speed up your Python programs without actually having to do much. You just have to be careful about how you write certain things. So this is the agenda. I'm going to go through all these different subjects. I'm going to start with the calls and the loops that you have in Python. So say you want to call a function. Then there are various ways you can do that, and as you've probably noticed, every now and then Python function calls are not really that fast, actually quite slow. This is one of the areas that we always try to speed up things so that CPython can run faster. Now if you call C functions that are exposed in Python, they are much faster, and as you can see with the timings here, it makes a difference. Of course, most object-oriented programs will probably use method calls, and method calls are even slower than the regular C functions, the regular Python functions, because they have this additional method lookup that you have to do in order to find out which function to call. So there's nothing really much you can do about this particular kind of method. You can try to use operators, for example, to speed up things a bit, because they are implemented as bytecodes in the Python VM. But overall, the situation looks like this. So if you can try to have Python call a C method or a C function to make things run faster. Or if you're just using simple types in your functions or methods, you can try to rewrite them using Python, which is very easy. You just have to provide it with a few annotations, and it generates C speed code, and that's really fast. So that was function calls. Next is loops. Basically you have two types of loops. One is you want to just iterate over a certain range, and the second one is you want to iterate over a sequence. So let's have a look at the sequences first. There are a number of ways you can run over a sequence. The first one, of course, is the for loop. Then you have the map function you can use. You have list comprehensions, and you have generator expressions. And I did some timing of all these different methods, and as you can see, list comprehensions are the fastest. So it's the very simple kind of approach to take there to make it run faster is to use list comprehensions for your code. Now this is for calling operations that are implemented in Python. So the op function in here is a Python function. If you do the same in C, then it runs a lot faster, but also the difference between the various approaches of doing these things become a lot more obvious. So list comprehensions really win in this case. Now the second topic is loops over ranges. So you want to iterate, say you want to call something 1,000 times or 10 times. This is typically done using the range function in Python, and range gives you back a list of, in this case, for example, 1,000 integers. Then there's a little known function called xrange. How many of you do know xrange? Okay, so strike the little known. Which is actually good, because if you compare those two, you can see that there's a huge difference between using range and xrange. So xrange just uses 40 bytes because it's a generator, and with the list you actually have to create the list, and it takes 32 kilobytes of memory. Runs a lot slower. So yeah, the obvious answer here, of course, is to use xrange. And because it's so obvious, it was changed in Python 3. So in Python 3, range is actually the xrange function from Python 2. There is a module called itertools. How many of you know itertools? Oh, that's very good. If you don't know that module yet, you should definitely have a look at the documentation. It's an excellent module for implementing things that you want to do in loops. If you can't use one of those, try to find some C extension that was written for your specific use case, and then try to use the functions defined in there. For example, if you're doing lots of math, you can use NumPy arrays. If you do image work, then you can use PIL. If you use XML, you use LXML. Or if you do text parsing, you can use, for example, MX text tools. So that's what you can do to speed up your program in that area. So next is sorting. There are two basic methods that you use in Python to do sorting. One is the sort method in Python, and the other is the sorted built-in. How many of you know the sorted built-in? Okay, not all of you. The difference here is that the lsort method actually does an in-place operation, so it changes the list that you're working on, whereas the sorted built-in, it creates a list copy of what you want to sort. Now the great thing about sorted is that it takes just an iterator as input, just so you can put in anything that you can iterate over, whereas with the sort method that you have on list, you can only operate on lists, of course. Now here's a typical way of sorting a list, for example, on the second item. So what you do is, or what you can do is, you use this decorate, sort, and then undecorate pattern. How many of you know that one? Very few. In Proland it's called Swatchian transform. Maybe you know that one. What you do is you, as you can see in the first part here, you decorate your list. So you create a new list that has the item that you want to sort on as first item in the tuple, and then in the second item you just put in the original entry that you have in the list, and you sort it, and then you undecorate it again. So you remove that item again, and you get back a sorted sequence. And you can do the same thing with sorted and the generator approach. Now, Python can do better on this one. It can use a key-based approach for sorting. So what happens is Python will then call a key function on every single element that you have in your list, and then just sort the keys. And then, of course, use the information that it got from where to move which item of that sequence for actually creating the real final list of sorted items. So you can do that either in Python using, for example, lambda function, or there's an operator module, and that operator module has a nice utility called item getter, which basically does exactly the same thing as the lambda function that you have in the first example. How many of you know this helper? Quite a few, that's good. The operator module has a lot of nice functions, so you should definitely have a look at it if you don't know it. This is the same example, but it tries to fetch an attribute of the objects that you have in your sequence. So it uses the last name attribute in this case. And again, you can see you can do it much faster using the operator module. So that's a tip that you can use in your code to make it run faster. Next is joining strings. You probably all know the two different methods that you can, or patterns that you can use for doing that in Python. Of course, you have the plus sign, so you can have you can concatenate strings to make bigger strings. That's good if you just have a few of those strings to concatenate, because every time that operator gets called, it does a copy of what it has and then adds something new to it. The second approach is using join and then a list of the entries that you want to join. And that, as you can see in this case, even if you have just 4 strings to join, it actually makes a difference. But it's a lot more obvious if you have many strings to join. Of course, no one would write the plus notation for 1,000 elements, but just for comparison, it's really the difference there is really enormous. And then there are some other methods you can use. One is the %sign formatting way. It's ugly, it's not really fast, don't use it. Then some people, sometimes on the mailing list, they mention, yeah, well, you can use the array module for doing the same thing. Yeah, it does work, but it's even slower. Or you can use the cstring.io module in Python 2 to basically then just write to an in-memory string and try to use that for speeding up things, but it doesn't really work. So those should not really be used. Right, next is lookups. So we're going to start with dictionary lookups. I did some timing there. I used a dictionary with integer keys and then one with string keys, and I found integer keys to be really, really fast. So if you have something that you can map to integers, for example, constants that you want to look up, then using integers as keys in dictionaries is really a good idea. If you have strings, the problem there is that Python always has to do the string comparison in order to make sure that the string that it fetched from the dictionary is actually the one that you want to use. There is a trick though that you can use to speed that up. You can intern the strings. How many of you know intern? Few. So intern is really nice in that it creates just a single copy of that particular string in memory. The downside there is that once you've interned that string, it'll never go away. So garbage collection no longer works on that string. But as you can see, the performance is a lot better. And the reason for that is Python uses this internally to do attribute lookups, for example. So it speeds up attribute looks up a lot by interning the attributes that you want to look up in your code. Provided, of course, that Python knows about the attributes, so it has to be in your C code, in the Python code that you write. Right. Next one is variable lookups. So obviously, global lookups are slower than the locals. So if you do the timing, there's a small difference that you can see there. Let's have a closer look at the global lookups, because there are some techniques that are being used to speed those up. So the general kind of approach that you do is this one. You just have the global there, and you just use it in your Python function, which is not really that bad, the performance. Then there's a trick that some people use. They put the global into a local variable by adding it to a function as keyword argument default. How many of you know that trick? A few. Well, as you can see, it doesn't make much difference. You have 81 microseconds here, and in this one is 85 microseconds. The downside here is that even though it runs a bit faster, it can also create bugs in your application, because people can actually pass in that argument to your function, and then of course your function won't work anymore. Then there is an approach to localize the global in your function. And as you can see here, it uses 90 microseconds. So it's slower if you just use it a few times. If you have a tight loop in there, then this makes a lot of sense. So for example, if instead of just using x equals local a, if you had a for loop in there using that global, then doing this does make sense. So you can try to use that. So these are the timings for the various lookups. If you can, use a local. I think that's what you can take away from that. Then the next type of lookup is attribute lookups. So you have a standard kind of class definition here. You have class attributes, you have instance attributes. And then if you time those two, you'll find something very interesting. It's that instance attribute lookups are basically the same speed as class attribute lookups, even though Python has to go from the instance to the class in order to do the class lookup, which is interesting. So what to take away from this is that it doesn't really pay off localizing the class attributes in your instances. You just take away more memory, so you don't have to use that. Now, I also compared the old style classes with the new style ones. How many of you know this difference between old style and new style? Okay, not that many. So some years ago, Guido went ahead and he tried to unify the two type systems that we have in Python. One is called the old style classes now, and all the classes that you wrote in Python were old style classes, and all the types that you used internally, like lists or dictionaries, for example, those were a separate kind of type system. And what we have now is we have a unification of those two, and those are called the new style classes. And as you can see here, old style classes actually do behave better in some cases. For example, the instance attribute lookup for old style classes is faster, and that might be something that we would want to perhaps improve in CPython. Then there's something called slot attributes. How many of you know that one? Okay, a few. It's very good. You should definitely have a look at those. This is an optimization that was added to Python a while ago. I think it was around the same time as these new style classes were introduced. This is a way to basically define your the attributes that you have in your class instances in a way that Python can optimize them. So you no longer create a dictionary for those, and because you no longer have to create a dictionary, the lookups are faster. The lookups don't have to go to the dictionary anymore, and you don't have to spend extra memory on a dictionary. So while this is not exactly, it's not really faster than dictionaries, it does make a huge difference in terms of memory usage. And I'm going to give a lightning talk tomorrow about this case with some interesting results. Right, the next one is exceptions. Now, exceptions are, or should be used in Python only for exceptional cases. So only when you actually write code that only fails in a certain small percentage of cases. You should never try to write code that fails often and then runs the exception case very often. And this is why. This is just an example. You use attribute introspection and you want to see whether a certain object has an attribute or not. And as you can see, if the exception triggers, and you actually have to go into that except part of the try except, it takes very, very long to run. Whereas if the exception does not trigger, it doesn't take long to run. So what can you do about that? Well, again, you can try to have Python catch the exception at C level, because at C level, it doesn't have to do all this, the frame logic that's normally needed to process exceptions. It can run much, much faster. And for example, in this case, you can use the getAttr built in to do the lookup for you, and that will catch the exception, that attribute error in C, and it runs faster, as you can see here. So this is just one example. There are other examples. There are many cases in Python where you have the option of either using a method or a function that actually creates or raises an exception, or you have this more or less the same kind of thing that returns, for example, none or some special value that you can then use to detect that exceptional case. So what's the conclusion? There are a few things that you can do, like you just saw, that you can do to speed up your code by just being aware of these things. And of course, there are a lot of things that you can do at a higher level in your application. The most efficient ways of doing these performance improvements is by using proper data structures for these things. So if you have a certain specialized case of where you need a certain, say a tree, for example, as data structure, then use that. You can use efficient algorithms. There are lots of books on that. And I would really urge everyone to have a look at those books, because the research has been done, the algorithms are there, they're not difficult to understand. There are even Python books that implement those algorithms, and you should definitely use them. And of course, you can refactor your code every now and then. Move loops to C, do profiling, and then maybe use Python, for example, to speed up your code. Right. That was it. All the resources are up on GitHub at that URL. All the tests that I ran are up there. There is a helper module that's kind of interesting. It's perf tools called. You can do the timing with those functions. You can do the memory checking with those functions. And if you need help, just contact me. Right, that was it. Any questions?
I don't know, Hi, can you recommend any frameworks for performance testing? The only one I've used was vBench, which was Wes McKinney's sort of thing. That was a part of Pandas, but we used that quite successfully because it could monitor your performance every time you check the code in, would run a whole battery of tests and plot it, and you could see over time if your refactoring was improving. Do you know of any other ones? Because vBench, I think, is a bit legacy now. I don't think it's been touched for a while.
Well, I mean, it's not really a framework, but you can just use the standard C profile module that you have in Python and just run your code using under that profiler, and then you get the output, and you can use that for detecting the hotspots in your code. I'm not sure whether that's what you actually meant with the framework, but
I was thinking of more larger scale tests than that sort of the whole system rather than a detailed.
Some of the testing frameworks that you have, they allow you to enable profiling while running the tests. Yeah, and you can use that for doing this. More questions?
I think back first and then you.
You mentioned Python. I'm just wondering if you've tried doing those tests with Number instead of Python.
No, not yet.
I recommend you do. From what I've been seeing from benchmarks of my own, Number makes Python run as fast as C.
Okay, it definitely gives that a try, yeah.
Similar to the first question, I wonder whether there are any load testing frameworks that you've used.
What exactly do you mean with load testing? Like what I did here with the range 1000 list as input? Or?
I was more meaning sort of, say it's a piece of server code than something for running lots and lots of requests against that server in parallel.
Right, well, for web server stuff, you can use the Apache tool, the AB tool, to do your benchmarking. And you can use that to generate the load and then do profiling maybe on your code. So for example, you can use that as input to generate all the requests and then have your C profile do the profiling on your Python code and then use the output of that to analyze your code. Yeah.
And then okay, well, I'll do. Who was it here? Yeah. I'll do you first.
What kind of project have you been, or what project have you been doing that's required all of these performance optimizations to be made?
Well, a few years ago, let's say that was 1997, I started writing a web application framework like everyone else at that time. And I wanted to have it run as fast as possible, so I did all these tests back then for Python 1.5.2 it was. And I thought this year I could basically do the same again for Python 2.7, and I found these values, and that was interesting.
Okay, in terms of that exceptions, isn't it more Pythonic to actually try something and fail over on exception and do something at that point? I know you showed one workaround for like a value error through that item getter, but there are other things, but I can't think of anything at the moment, but I know like I've done that in so many parts of the code where you try, fail, and on that exception you actually have a block of code. So you code by exception, which is more Pythonic apparently. So is there any other way to actually work around other than using the one option you showed for value error?
Well, I mean, these are just performance hints or tips. Yeah, these are not general kind of design recommendations. You should not always write your code in a way that it makes it most performant, because it usually becomes less readable that way. But if you do have a case where you actually want to speed up your code, then you should definitely have a look at these things. So I'm not saying that's not the point of the talk to write your code in a way that just goes through hoops to make things run faster and then less readable. So that doesn't really make sense. More questions? No? One more. And then Larry. What is setup? Yeah.
I was actually wondering, does it make a lot of difference how deep in the stack an exception is raised before you catch it? Say if it's like 10 functions deep and you call it, say, at the root, or if you call it like earlier on, how much difference that makes?
That's a good question. If you're doing that in Python, it might make a difference, because, but I really have to check that, because I don't know whether the traceback is actually being generated when you enter the accept part of the code in Python. If Python has to generate the traceback at that point, then of course, yes, a deep stack will obviously take more time to generate that. If it doesn't have to generate the traceback, then it probably doesn't make any difference.
All right, thanks. Okay.
All right, thank you.
Thank you very much.